Greetings. Let's talk about the stability. Last time we saw that a negative feedback system such as this can become unstable under certain conditions. And we wrote the closed loop transfer function in this form. So it's just the forward transfer function h of s divided by 1 plus the loop gain. And then we said it is possible that the loop gain becomes equal to -1 at some particular frequency. We are considering only imaginary frequencies, and that corresponds to sinusoidal signals. And we say, okay, suppose that S is equal to j omega 1. And what's happening is that beta h of that S value is equal to -1. So we see that the denominator is 0, the numerator is not. So the transfer function from x to y goes to infinity, and the circuit is capable of oscillation. All right, so for amplifier design, we don't want that to happen, which means we want to make sure that at no frequency do we have this condition valid. All right, now I'm going to slightly modify this condition as follows. I will write this in the form of two equivalent conditions. And this is because remember that for any complex number, we also have this polar representation. We have the magnitude, which is a plus jb, and that's a squared plus b squared. And then we have the angle, which is tan -1 of b over a. So I say, okay, that means that the magnitude of this quantity must be equal to 1. And the phase of this quantity must be equal to 180 degrees, plus or minus, doesn't matter, 180 degrees. So from now on, anytime we want to study stability of a negative feedback system, we examine these two conditions. And we will decide whether there is a frequency at which both of these conditions occur. If they both occur at the same frequency, then the system can become unstable. All right. Now, for what we'll analyze soon, let's go ahead and consider some cases. Let's start with this case on the right-hand side. It's simpler. We're going to plot the magnitude on this plane here, and then the phase on this plane here. For the magnitude, if we want to be precise, we go with log-log scales. So this is 20 log of the loop gain, and this is log of the frequency. For the phase, we just plot the phase. All right, so the key point is that this unit is in dB, and that means that the 0 dB is equivalent to a gain of 1. So let's follow this frequency response and see what's happening. At low frequencies, we have some value here, and this keeps rolling down. And at this frequency, we see that the gain, the loop gain, beta h, has dropped to unity, to 0 dB. So we have a name for this. We call this the gain crossover frequency. Just a name. And that means that loop gain has just passed 1. Now about the phase. Well, the phase has some behavior we don't exactly know, but it's possible that at some frequency, the phase reaches -180 degrees. And this frequency has a name too. This frequency is called the phase crossover frequency. Frequency, let's clean this up, frequency. Okay, so that's the phase crossover frequency. All right, so the question is the system stable with the illustration that we have here? Now, to determine that, what I will do is I'll start with this phase of -180 and find the frequency at which that occurs. So the frequency, I just follow my plot and I say, okay, I go this way, I hit the plot, I go up here, I have this frequency. All right, so at this frequency, the phase of beta h, meaning this phase from here to here, you can think of it as delay or phase shift, has reached 180 degrees. Now I continue on this line and find this value of the loop gain at that frequency. we see that the loop gain is less than 1. It's this value here. And that means that at this frequency, we are not satisfying these two conditions. It is true that the phase is 180 degrees, but the gain is less than 1. So the circuit cannot oscillate, and that means that the circuit is stable. So that is our approach. Let's try that for the illustration on the right-hand side, this one here, and see how that works. Now, I need to go back and slightly modify my conditions, these two conditions here. So we said that we're looking for a frequency at which the loop gain is 1 and the phase is 180. Well, it turns out that the system can be unstable if the loop gain is 1 or greater than 1. So both of those lead to oscillation, provided that the phase is 180 degrees. So we won't prove that here, but we just accept it. Okay, so now let's go to the system on the right and see what's happening. Okay, so we're coming down. At this point, the loop gain has dropped to 0 dB. So this is what we note by omega GX, the gain crossover frequency. And the phase reaches minus 180 degrees at some frequency. We call that the phase crossover frequency, and denoted by omega PX. So is the system stable? Well, okay, I'll just follow my technique. I start at minus 180, I travel this way, I hit the phase plot, then I go up, I find the frequency at which the phase is minus 180. Then I ask, at that frequency, what is happening to the loop gain? So I go up here, and I see that the loop gain is this much, which is more than 0 dB, so it is greater than 1. So we see that at this frequency here, we are satisfying both of these conditions. So the system is unstable. So overall, we can summarize as follows. If omega px, meaning the phase crossover frequency, is less than the gain crossover frequency, then the system, or equal to, then the system is unstable. If you go back to this stable system, we see that's the other way around. The gain crossover frequency is here, this one. The phase crossover frequency is here. So the phase crossover frequency is greater than the gain crossover frequency, and that indicates a stable system. Okay, so that's how we go about analyzing the stability of a system based on the Bode plots, or the frequency response, for both the magnitude and the phase. And of course, at the transistor level, at circuit level, we can always construct these. It is important not to confuse this quantity, beta h, which is just beta times h, the forward transfer function, with the closed loop system transfer function, this one. So we are predicting the stability of the closed loop system from the properties of H and beta. We can think of H as the open loop system. So one must not confuse these plots that we are showing here with the transfer function from X to Y. We are not plotting this transfer function. We are plotting only beta times H. All right, now, as we begin to go into circuits, etc., we need a method to draw these two responses accurately to some extent, both for the magnitude and the phase. So for that, we resort to Bode's approximations, which are very nice and efficient. So here's what Bode says. Bode says if we approach a pole frequency, then if we approach a zero frequency, then the magnitude slope increases by 20 dB per decade. If we approach a pole frequency, the magnitude slope decreases by 20 dB per decade. Also, Bode says that the phase, meaning this phase here, this phase plot here, begins to change at 1/10 of these critical frequencies. So if we are at 1/10 of, let's say, pole frequency, the phase begins to become more negative. And at the pole frequency, so by minus 45 degrees at the pole frequency, so it changes by minus 45 degrees right at the pole, and then approaches minus 90 degrees at about 10 times the pole frequency. For the zero is opposite. So if we have approaching zero frequency, at the zero frequency, we have plus 45 degrees of change. And at about 10 times the zero frequency, we have plus 90 degrees of phase change. So let me illustrate these points by the system on the left-hand side. This is the first order system. So here's what we have. We have beta H is equal to, let's say H. The forward transfer function, going back here again, right? The forward transfer function is just H is A0 over 1 plus S over omega 0. It's a simple first order system. It has a low frequency of gain of A0, and it has a 3 dB bandwidth equal to omega 0, a pole at omega 0. So, all right, so at very low frequencies, we have only A0. So that's, if you're plotting beta H, this would be beta A0. And travel this way. Now, as we approach the pole frequency right here, Bode says the slope should decrease by 20 dB per decade right here. So this slope now is minus 20 dB per decade. And it keeps going. How about the phase? Well, Bode says that we should start changing the phase at 1/10 of the pole frequency. So let's say we start at low frequencies. At low frequencies is very small. We don't have any phase shift, so we are here. The phase shift is 0. And as we go to slightly higher frequencies, let's say at 1/10 of omega 0, we begin to see a change. And then at the pole frequency, the phase changes by minus 45 degrees. So we are right here. And then at 10 times that, so roughly around here, 10 omega 0, we have a phase of approximately minus 90. Not quite, but approximately minus 90. And that's the number that we have here. So this nicely allows us to plot the magnitude and phase of any transfer function as long as we know the positions of the poles and the zeros. So it's pretty quick and clean. Okay, all right. Let's go one step further and consider a system that has 3 poles. So this would be a system like this, H, and has 3 poles. You can see that one here, one here, one here. So something like 1 plus S over omega P1, etc. Okay, so we just follow what Bode says. Bode says we reach a pole, the slope decreases by 20 dB per decade, so it's minus 20. We reach the next pole, it decreases by another 20, so that's minus 40. We reach the third pole, it decreases by another 20, so that's minus 60. These are all dB per decade. So 20 dB per decade means the magnitude changes by 20 dB, factor of 10, for a decade of frequency change, meaning if the frequency changes by a factor of 10. All right, how about the phase? Well, we follow the same procedure. We say at low frequencies, we don't have any phase shift. At 1/10 of omega P1, it begins to change. At omega P1 is minus 45 right here. At about 10 times omega P1 is about minus 90. At 1/10 of omega P2, which would be somewhere around here, it begins to change. At omega P2, we have another 45 degrees from that. So that would be minus 135 right here, minus 135. You have approximately 90 from the first pole and 45 from the second pole. We are assuming that these poles are far from each other so that we have this nice phase profile that you can see. All right, we continue. At 10 times omega P2, we have minus 90 from omega P2, minus 90 from omega P1, so it's about minus 180. And again, right below omega P3, we have another 45 contributed by omega p3. So here we have minus 180 minus 140, minus 180 minus 45, so minus 225 degrees. And then if you go on to about 10 times omega p3 contributes minus 90. So we have 3 poles. We are far from all of them. So all of them contribute approximately minus 90. That's why we get approximately minus 270 degrees. So this is how we plot the frequency response, both for the magnitude and the phase, using Bode's rules, if we know our poles and zeros. I will see you next time.